Hello, Algebra 2 students. I hope that you are doing well. I'm out testing this week and I thought that I would make you a video of lesson 6.07. This is my second take. I did the whole entire video and then the app that I'm using only allows me to make 30-minute videos and I was like 2 seconds over the 30 minutes. So I am re-recording and I'm going to skip the do now to save some time. I'm going to talk about the announcements for the week. Monday we had no school. Tuesday 606 quiz. I was out of the office testing. Wednesday 607, Thursday 608. I'm out of the office testing and Friday is a catch-up day. This screen, this bright yellow screen, is going to give you just a little bit of information about an assignment that's coming up in your future. So this is a future assignment. This is 6.12. I should have put this on my slide, but I did not. This is examples of the 6.12 unit test, part 2. This is actually coming up. It is November the 1st. So I just thought I would stick this in here. This is not one of the hardest TGAs you've ever done. There's really just one thing in particular that I wanted to talk about that, and that is number 1. So it looks like this says these are examples of number 1 and number 2 on your unit 6 part 2. We've got a graph to refer to over here. Number 1 says, is the function discrete or continuous? Well, the answer to this one is continuous. And I'll talk a little bit about both graphs. But this graph is continuous because once you put your pencil down, you'll draw the entire graph without picking up your pencil. So continuous, meaning it's continuous, okay? You're going to continue, as soon as you put that pencil down, the entire graph is drawn with like one stroke of your pencil. So other things that are continuous, I'll just abbreviate here. Lines are continuous. Parabolas are continuous. I know I'm picking my pencil up to put the arrows on the end, but it's just talking about once you put your pencil down and you draw the entire graph, it's continuous. Cubic functions are continuous. This is an exponential graph, so growth and decay, those are all continuous. So if it went like this, it would also be continuous. All right, discrete. We don't see a lot of discrete graphs. We honestly, if I think about all the graphs I've ever seen, most of them are continuous, but we do study graphs that are discrete. So for instance, when you were in the 6th, 7th grade and you were just plotting points, so a graph that just had plotted points, that would be discrete because you had to pick up your pencil several times. The graph was not a continuous, it was not continuous, it was not connected by a curve or a line. Later on in Algebra 2, we will actually look at graphs. We've seen a few of these in the Do Now that are just like little pieces of graphs. So I'm having to pick up my pencil to actually do this. These are called piecewise functions. So discrete, to me, the way I've always remembered it is anytime you have a graph that is discrete, you're having to pick up your pencil. You're not drawing the entire graph with one stroke. So number 1 says, is this function discrete or continuous? We're going to answer continuous, and it says explain. So we're talking about this graph, and I would just say something like the graph never stops. It can be drawn. With one stroke, something like that. I'm sure you can look up discrete and continuous and get a more complicated mathematical definition for that, but that's just kind of what I go with. Number 2, let me erase this. Number 2 says identify the y-intercept. So let's find that. It's located here. And it's also reminding you to write as an ordered pair. So some of y'all have been forgetting to do that on your TGAs. So this crosses the y-axis at +1. And so the ordered pair for that y-intercept would be 0, 1. Number 3 says, is this an example of exponential growth or decay? So this is growth where it's rising from left to right. And then this would be an example of decay where it's falling. So this is definitely growing from left to right. So this would be growth. So you would answer growth. And then it says, how do you know? You could say things increasing from left to right. I've seen y'all say things like, as X increases, Y increases. Y'all are pretty good about identifying that. I've not seen a lot of mistakes on that. The example 3 on the Unit 6 Part 2 is going to deal with using either the growth formula or the decay formula. So just remember those are exactly the same. The growth has the plus R in it. So for instance, it could say the duck population in Athens, Alabama started out at 727 ducks in 2010, and it's growing. The population is growing at a rate of 7%. How many ducks will there be in 10 years? Something like that. So you would pick the growth formula. An example of decay would be, let me think about something that goes down. Your bank account started with $1,200. You are spending at a rate of 25%. How long will it take, or how much money will you have in your account after 6 months? Something like that. So something that shows that it's decaying, going down. So you would make sure that you use your minus. Remember, A is your beginning amount, R is your rate as a decimal. So for instance, if it said your rate of increase was 5%, make sure you move the decimal 2 places to the left and use 0.05. And then I put T for time. I know these have X's in them. So this really should have been an X. X is your time. Okay, so just a little commercial about 6.12 Unit Test Part 2 coming up in the future on November the 1st. Not a hard Part 2 compared to some TGAs, compared to some that you've done before. This lesson that we're going over today, 6.07, is using logarithms to solve exponential equations. There are some optional things for you to do. They're on slides 10 with answers on 11, practice problems, ACT problems on slide 12 with answers on slide 13. All right, jumping right in. Let's solve this equation. I know it's an exponential equation because I do not see log or ln anywhere in the problem. So let's go over our steps. Step number 1, isolate the base. Step number 2, take the log of both sides. Step number 3, use properties of logs to isolate the variable. Step 4, solve. So our bases are 3 because that is what's raised to our exponent. So I'm going to put a box around it. That's what we're isolating. This 2 is being added, so I'm going to subtract 2 from both sides. That's going to give me 3 to the x is equal to 15 minus 2, which is 13. So that's step number 1, isolate the base. Step number 2, as long as my base is not the letter E, okay, I am always going to use log logs, common logs. If my base is E, then I'm going to use ln, natural logs. So my base is not E, it's 3. So I'm going to take the log of both sides. So we're going to become lumberjacks, and we're going to be working with logs here. All right, so take the log of both sides. That's technically legal as long as you take the log of both. Then we're going to use properties. So I'll tell you one of the main properties that we use when we're solving exponential equations. I'm just going to write this main property. We use this a lot is the power property. It's not the only log property that we use, but we use it a lot. So that's what I'm going to use next. Let me change colors here. My variable that I'm solving for is in the power spot. It's in the exponent spot. So that power property says I can take that power, I can bring it out in front of my log, and I can multiply it times my log. So my next step is going to look like this. X times log of 3 is equal to log of 13. And the reason that's helpful is it's really, 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 really difficult to solve for a variable that's in the exponent spot. So if you can get that exponent out here, then we know it's being multiplied times log of 3, so we can divide both sides by log of 3. And then that's going to give me my x value. And then I'm going to use my handy dandy calculator to do the rest of this. I'm going to pick it up just so I can go through the motions here and to make sure that I'm giving you proper instruction. When you do log of 13, so when you hit your log button on your calculator and you put in 13, my calculator opens up a left-hand parentheses and then you enter in 13, and that's always a good common practice to close the right-hand side of that parentheses. So I'm going to do log of 13, close the right-hand side parentheses, divided by log again. The left parentheses opens on the 3, put the 3 in, and then close the right-hand parentheses. So it's going to look like this when you enter it in your calculator. And then usually we round to 4 places. You just follow the directions on rounding, and that's going to be 2.3347. Now I want to go back to this step, and I want to talk to you a little bit about why we had to use logs. So if I had 3 to the x is equal to, instead of this being 3 to the x is equal to 13. So let's say it was 3 to the x is equal to 9. Then would you not agree that x would be equal to 2? So back in 7th grade, 8th grade, Algebra 1, when we were solving exponential equations, we were looking for exponents that were whole numbers. But in this problem, this says 3 to what power is equal to 13. So I just can't come up with what that power is, because that power is going to be a decimal. So let's think about our answer. Let's think about this answer. So the question was 3 to what power equals 13. So let's see if we're right. 3 to the 2.3347. Keep in mind we rounded that, so that's not the exact answer. And we're trying to see if that's equal to 13. So if I take my calculator and I take 3 and I raise it to the power of 2.3347, that is going to give me 12.999749979, which is really, 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 really close to 13. And that's okay that I don't get 13, because I know that this is a rounded answer. And if I use the exact decimal that never ended and never repeated, then I would get exactly 13. So just for you to kind of think through this, and I know sometimes you're learning all this math and you're thinking, why am I doing this? Who created it? This is just absolutely ridiculous. But there are some exponential equations like this one, so like 3 to the x is equal to 13, that we can't solve without using logs. So that's why the logs were developed. They were developed to solve exponential equations that we cannot solve on our own. So hopefully that was helpful. I do like to kind of explain the why, and hopefully that'll help make things make sense. Oh, and by the way, we did solve here. Okay, example 2. Another exponential equation. We've got 10 to the 5x. That is our base. So we're going to isolate our base. It's already isolated. Okay, so we don't have to do that part. We're going to take the log of both sides. Since this is base 10, we're going to use log for every single base unless the base is e. And I do have an example where the base is e. So we're going to take a log of both sides. So we have log 10 to the 5x is equal to log of 30. Now this problem actually has a shortcut, because I do have something that simplifies. So I'm going to put a little happy face right here. My log, remember, is a common log, and it has an understood base of 10. So when your log, okay, has the same base as what follows it. I'll say that again. When your log has the same base as what follows it. That did not happen in example 1. So let's go back up here. This base is 10. The base of my log is 10. The base of what follows it is 3. So what's going to happen in example 2 could not have happened in example 1, because the base of my log was not the same as the base of what followed it. So in example 2, since I have log base 10 of 10 to the x, these logs are going to cancel. So I'm going to go over here for just a second, just so I don't lose you. But if we have log base 10 of 10 to the 5x, we did this in the first part of Unit 6. We simplified logs. So this really means, this 10 means 10 to what power is equal to 10 to the 5x. So this log actually simplifies down just to be 5x. So that means log base 10 of 10 to the 5x means 10 to what power is 10 to the 5x. So this side just simplifies down to 5x. So you get a little happy in your problem or something actually simplifies that you didn't really intend to. Now you could continue to work the problem like you did example 1 and use the power rule and bring the 5x out to the front, but your problem's just going to be longer. So knowing that this side simplifies is a smart thing. And then we use properties. We really didn't have to use properties here because the log simplified on the left-hand side. So then we're still solving for x, so we would divide both sides by 5. And then x is going to equal to, don't forget to put parentheses around your 30. And log 30 parentheses divided by 5, round 4 places unless they tell you otherwise, 0.2954. And just to kind of double check, and I did round here, so I should have wavy lines. All right, y'all, hold on just a second. I'm getting a authenticate my computer. I don't want it to turn off while I'm making this video. Hold on just a sec. If you're testing this week, or if you've already tested, I hope you had a good experience, or if you're going to test, I hope everything goes well. All right, example, oh, and we did solve. All right, example 3. This one has an E in it. So if you'll notice in my bright yellow box, I've said use LN, which stands for natural log, when working with a base of E. This is just my rule. You can use LOG. It just usually makes your problem longer. So somewhere along the way, probably Miss Haynes, my math teacher that I had for 3 maths in high school, she probably taught me this. So we're still going to isolate our base. So E is our base that's raised to the -3 exponent. So we're going to do that by adding 3 to both sides. That's going to leave me with E to the -3x is equal to 2 plus 3, which is 5. We're going to take the log of both sides. So since this is a base E, I'm telling you that it is best practice to use the LN of both sides. So we're going to take LN of the left. We're going to take LN of the right. And we're using logs because we can't solve this problem without the logs. Now, we get a little happy here. This was just like in example 2. The understood base of this LN is an understood E. So if I have LN base E of E to the -3x, that means E to what power is E to the -3x. So this side is just going to simplify out to be -3x. And you don't have to use any properties of logs to solve from this step forward. You're solving for x, so we'll divide both sides by -3. Put the 5 in parentheses. We'll do LN. LN is on your calculator. LN is below log on my calculator. LN 5 parentheses divided by -3. And I'm getting -0. I'm going to round 4 places, 5365. 5365. If you get any type of errors, sometimes when you're doing LNs and LOGs on your calculator, you could get some type of error that probably just means you made a human mistake typing it in. It could mean that you've set something up incorrectly, but that happened to me earlier when I was making my first recording. All right, last example, example 4. So isolating our base. This one's just a little bit harder. It's got some more steps. So this 2 to the 3x minus 1 is my base. So I want to get it by itself. So I'm going to subtract 24 from both sides. That's going to leave me with 2 to the 3x minus 1 is equal to 36 minus 24, which is 12. I can't figure this out. 2 to what power? 3 times x minus 1 is going to give me 12. 2 to no power is 12. So that means x is going to be a decimal here. So I am going to have to use log. So let's take, since I don't have base E here, I'm just going to use my common log LOG. So I'm going to take log of both sides. This one's going to be harder because I've got this binomial in my exponent. then I am going to have to use some properties here. I'm not going to get a happy and something just cancel out. So I'm going to use the power property again. So I'm going to take this power, all of that's my power. I'm going to bring it out in front and I'm going to multiply it times my log. Since I do have more than one term, I am going to put the 3x minus 1 in parentheses, and that's being multiplied by log of 2, and that's equal to log of 12. I am going to have to distribute my log here. So I'm going to get 3x times log of 2 minus 1 times log of 2, which will just be minus log of 2, is equal to log of 12. And then I'm going to find my x. It's right here. So I'm still solving. I'm in this step right here. So I'm going to add log of 2 to both sides. That's going to give me 3 times x times log of 2 is equal to log of 12 plus log of 2. And right here, I have two logs that are being added together, so I can use another property. Okay, I can use the product property. That's going to combine these two logs, combine, condense. Both words kind of mean the same thing in this situation. So my product property, let me write that down. I'm using my product property. Anytime I have two logs that are being added together, I can rewrite that as one log. As long as that's a plus, then I multiply the 12 times the 2. If that were a minus, then that would be the quotient property, and I would do 12 divided by 2. But since that's adding, that's the product property. So I'm going to do 12 times 2, which is 24. I'm going to continue to solve. I'm trying to get x by itself. So I'm dividing both sides by 3 log of 2. And then I'm going to overdo my parentheses. So if I'm going to enter this straight into my calculator, I'm going to use black here. I'm going to put parentheses around the 24 because it follows the log. I'm going to put parentheses around the 2 because the 2 follows the log. And then because I have a whole bunch of crap in the denominator, I am going to put parentheses around everything that's in the denominator. So this is exactly what it's going to look like when I type it in my calculator. So I'm going to do log, parentheses around the 24, divided by left parentheses to show I have a bunch of junk in my denominator, and I want to keep all that together. 3 log 2, parentheses around the 2, and then another parentheses right here to close up what's in my denominator. And that's going to give me approximately 1.5283. All right, hopefully this was helpful. That is my last example. If you want to try some problems, there's some for you to try. There are the answers. Here's some ACT problems. Yep, these look like log problems that I found on an ACT practice test. I hope this helped you. Again, this is 6.07. Don't forget to save your whiteboard. And I'm not doing any exit tickets while I'm out this week making these recordings. So please don't send me any of those exit ticket by emails. I'm not going to have time to grade all those. So just no bonus points for exit tickets this week since I'm out testing. I hope this was helpful. I know that I went fast, but this was my second take because I took too much long on the first one, and it would not process. My video would not process. If you need anything at all, please email. I will be trying to check my emails in the morning before testing and during my lunchtime, and if I have any breaks, but that's not promised. Sometimes we'll be in rooms testing and we can't have a computer. So we'll get through the week. I